So today we're going to go over linearization. So linearization, if f is differentiable at x equals a, then the approximating function L of x equals f of a plus f prime of a times the quantity of x minus a. This would be the linearization of f at a. So basically what this is saying, for as long as the line remains close to the graph of f, okay, and I did not draw that very well, but let me try again. So let's say we have a function f, and we're drawing a line. There we go. Okay, then L of x, let's call this L of x, gives a good approximation to f of x. All right, so usually L of x is an approximation. It's the standard line approximation. Of f at a, where a is the center of the approximation. So x equals a may be, all right, referring to x equals a here. But you may be asked about, let's say, a plus 0.1, or even smaller than that, 0.001. So whatever it is, this line is going to give approximation to whatever f of a plus 0.01 is, all right? And so that's why finding this line is so important, because we can use it for our values, even if it's a minus 0.001. So for finding the line, and it is important, that gives us example number 1. So let's do that, and we can go on from there. Okay, so I just want to reiterate how a is the center of the approximation. And in our example, the value of a is 0. A lot of times it is, but not every time. Okay, so that's why we're using it in example 1. It says to find the linearization of f of x equals the square root of the quantity 1 plus x at x equals 0. So what we're going to do is find f prime of x, because we do need to have the derivative. It's the slope in our line. And so if we use our power chain rule, we now need to know what it is when x is equal to a. So we just went over how a in this problem is 0. So actually, let me change that to a 0 and continue. So we get that this is just 1/2. We also need x minus a. That's okay, that's just a simple substitution. But we need to add f of a. If you remember the point slope equation of the line, y minus y sub 1 equals m times the quantity x minus x sub 1. Well, you would have to add over the y sub 1, and so you could get y by itself. Well, this is essentially doing that already for you, and that's why it's so important to know that point slope formula, because you can actually use that to get L of x, your linearization. All right, so we need the y value for when a is 0. So we plug in 0 for x into our function. And now let's actually pull this all together with our form. So L of x equals 1 plus 1/2. Oops, that's supposed to be neater. Let me fix that. Times the quantity of x minus 0. So basically we're getting L of x equals 1 plus x over 2. Okay, and if you graph this with your original function, you can see how close they are, and not exact, but you can see when x is 0, how close they are. So I just wanted to show you what that looks like on the graphing calculator. I did a zoom 4. You can zoom in closer when x is 0. But I think this kind of justifies that, yes, the line is very close to our curve, so we can use that for an approximation. Now, I'm going to give you a table for the approximation, but you may be wondering, okay, why do we need this? So sometimes we're given a value, and let's say we need like 2 radical 2. Right, especially or 3 radical 2 or something like that. We're working with trigonometry, we see these radicals, and we need to plot a point, but we don't know the decimal without our graphing calculator. So perhaps we can use this approximation to get us close to that value. So if we needed to know the square root of 2, we can use this function and that linear approximation, okay? So if you see, the x value would be 1, all right? So if we use the linear approximation and plugged in 1 for x, then we can see we're getting 1.5. That's 1.5, okay? So we're saying that the square root of 2 is approximately 1.5. Now, in reality, the square root of 2, just the tens place, is 1.4. That's not much of a difference, okay? So that's a very good approximation, okay? Even though it's 1 whole unit away, it did help us here. Usually it's not, so let me give you that table of approximation. So hopefully this justifies, well, this is one of the applications we can use it for, and we can see how other problems may be asked in calc, so we can use it. Okay, so let's say we're given, or we're just curious about these x values for that function. So that means that we want to know what the square root of 1.2 is, or the square root of 1.05, or the square root of 1.005. These are your true values, okay, like how much off it is. So if you want to use the linearization to see how off it is, I don't know if off is the right word, maybe not. There was supposed to be an equals in there. Yeah, that's okay. All right, then it's a 0 at the end there. So if we were to figure out how much it differs by, and this question may be asked, so I'm going to put it in quotation, differs by. What we want to do, I'm going to erase the calculator, hold on. Okay, is to your true value minus the approximation. And take this absolute value, because we don't need the sign to see how far away it is, okay, because then it's kind of like a measurement. So if we were to do that, okay, we would end up finding that for the first one, that it differs by less than 10 to the negative second power. Okay, that is 0.01. I don't think that's too bad. This would differ by less than 10 to the negative third power, so it's less than 0.001. And this is less than 10 to the negative fifth power. If you put that in a calculator, it actually gives it back to you in scientific notation. So, yeah, it's really, really small. Like, the smaller it is to when x is 0. This was a little bit further away, so it differed slightly, but not as much as it differed here. So the linearization is a very good way to approximate our answer for, I guess, these values. So let's take a look at our next example. Okay, so in this example, we're using something different. Okay, it's to find the linear approximation when we know that x is approximately 0. We can use this kind of little formula here. So this is the most important linear approximation for roots and for powers. Okay, roots can be expressed as a power, so that's why I said roots and powers. Okay, and believe it or not, the first one we did already. Okay, notice that in the first one, our linearization, L of x, was 1 plus 1/2 x. So the 1/2 is the k that's described, and if you had to rewrite this, instead of a square root, you would use the power of 1/2, so that's what k is. So really awesome that if we could write it as an exponent, we can just use this form. Just be careful if it's not 1 plus something, so that brings me to the next one. And also to just want to emphasize x is about 0. Again, you can also say that it's centered at x equals 0. So in the next one, let me use a different color to start off. F of x is the quantity of 1 minus x to the negative first power. Okay? So if we need to rewrite it as this, we actually need to kind of rewrite it so we see that it's 1 plus a negative x and to the negative first power. Now, that may be very simple, but the reason for that is because our approximation is going to be 1 plus k, and the k is from here. Let me go back to the red. Times x, but it's not just x. Okay, we just labeled it as negative x. And then that will simplify to be 1 plus x. So that is our linear approximation. I tried to actually put the approximate symbol there, it came as an equals. It actually doesn't matter, but this is actually stated with an approximate. So if you do see a little wiggle there, it was meant to be there. So let's do the next one in blue. Okay, so this is the quantity of 1 plus 5x to the 4th to the 1/3 power. So there's a 1 plus, but it's not just x, it's 5x. Oh, I kind of circled too much here. Let me try it again. 5x to the 1/4 power. Wait, it's not 1/4. It was. Let me erase this and try this again, all right? Tiny bit better, I hope it helps. So, here we have not just x, but 5x to the 4th, and our k value is 1/3. So L of x would be approximately 1 plus the 1/3 times the 5x to the 4th. So that becomes L of x to be approximately 1 plus 5/3 x to the 4th. So fun, right? Just a rewrite. You do have to memorize this formula, and again, this is when it's centered at x equals 0. Trying to make some room for the last one. Okay, so here we go. The last one. So f of x is going to be rewritten as the quantity of 1 plus a negative x squared, and all of that quantity is raised to negative 1/2 power. Okay, so let me try to highlight here. The linearization would be 1 plus the negative 1/2 times the negative x squared, so that becomes 1 plus x squared over 2, and we're done. Okay, I know you thought we were done, but just one more problem. Okay, and I like this problem because it not only asks for linearization, but it says determine if an overestimate or underestimate, if it is an overestimate or underestimate by using concavity. So in previous problems we talked about concavity, and if we draw in the tangent line, is it an overestimate or underestimate, especially when we went over AP questions. So let's first find what L of x is. And we first figure out f prime of x and f prime of whatever a is, in this case pi over 2, which turns out to be, that was supposed to be a pi, negative 1. And we need f of pi over 2, and that turns out to be 0. Okay, so if we use this information to find our linearization, then we're just doing 0 plus negative 1 times the quantity of x minus pi over 2. So quite simply, L of x is, or approximately, negative x plus pi over 2. Okay, if you can read that, that's pi, that's a 2. Let me box that off. Okay, so now, if you look at the curve of the cosine of x, so this is why it's a common function. You need to know how to sketch its graph, okay, or know its graph when x is pi over 2. Okay, so this is actually at a 0, and then at pi, it goes down to negative 1. So if you were to draw in a tangent line, okay, it depends on where your value is for x. So if it's less than pi over 2, then it's along the curve that is concave downwards. So you can see that it's an overestimate, okay? And if it was below, or I should say, where the values are more than pi over 2, you can see how below the x-axis it's concave up. So this would be an underestimate because it falls below the curve. Okay, and so that's pretty much your answer here. That's how you would determine that. And I'm sorry, that doesn't look like the word over. Let me write estimate underneath. Hopefully that helps you understand how concavity and our lines help us. And let's do some practice.